Dan is now the Patterson Rockwood Professor of Energy at Harvard University. He's widely recognized as a leading researcher in renewable energy. His group has pioneered studies on several breakthrough technologies, including, I guess, notably the artificial leaf, which I don't think he's going to talk about today. He's won numerous awards, the ENnie Prize, the IAPS Award, the Berghausen Prize, the Elizabeth Wood Award, the United Nations Science and Technology Award, the Harrison, Howe, and Remsen Award from the American Chemical Society. And he's a member of the American Academy of Arts and Sciences, the U.S. National Academy of Sciences, and the Indian Academy of Sciences. You'll have to explain that.
Yeah.
So if everyone could join me in welcoming my friend Dan Nocera.
Okay, so thank you, Michael. And then we're going to do this like economic style, right? Not stodgy science style.
Correct.
Good.
People will talk.
When you feel motivated, talk. All right, so I'll talk today. So what I want to do first is give you a feeling of my biases. So if you do energy, you should always know everybody's biases. So I'm going to tell you bias, and then I'm going to tell you sort of how I choose problems, and I'm going to talk about 3 of them in terms of science. And I also then want to talk about models. Luckily, I've been able to interact with investors and people like that and find out what doesn't work. So it's very hard to move any energy technology quickly to market. And it's mostly because I was talking to Elizabeth. She actually has a number. I've always been guessing at the number. But just in the fossil fuel-based economy, a paper will be coming out from her that says it will cost you around $8 trillion. You've spent $8 trillion on your immediate fossil-based economy infrastructure. And if you spent $8 trillion, you've also paid it off. And so anything that we do as scientists, you're coming up against an $8 trillion paid off investment. And so when you start thinking like that, you realize all the complexity of trying to get an investor with an ROI of 3 years, right? So I think I tried a new model and it worked. And that was in the developed world. And then in the developing world, I want to try a new model in the next 3 years. And I'm going to talk a lot about that piece rather than the science that I do, even though I'll present some of the science and discoveries. So this is the energy identity equation, the simple one, which just says that energy is the same as, once I know population, GDP per N, and energy intensity, I can make a prediction or calculate energy. And so I did this in 2006 in Proceedings of National Academy of Sciences, and we calculated things out in this equation. And I want to talk about that today because I've used this equation as kind of a guide to choosing research problems. And that will become apparent in a minute. The second thing is this equation led me, once I moved to Harvard, to start a new epic. So at MIT, you can just do science and be totally happy. And that's all they expect from you. Once you move to Harvard, there's this whole other layer of BS that you have to deal with. And just doing science, they don't even care. I mean, it's like, what's a scientist even doing on our campus? And so I immediately recognized the challenges of being at Harvard and decided I would start a new epoch in humankind. And so you've heard of the Anthropocene. And what this is, I'm calling it the Sustainocene. And when we think about sustainability and environmental integrity, you think like that. Pictures of the blue earth and the globe and how everything's green. But my contention with this is that can exist if you have poverty. And it gets back to that equation. So if you really want to have a sustainable earth, you have to eliminate poverty. And you have to certainly eliminate the imbalance between in poverty, the haves and the have-nots of the world. And unfortunately, I think most of science is done for the wrong part of the problem, which I'm going to talk about today. And it goes back to this equation, and it's mostly due to this population driver. And that population driver, when you work this equation out, if I say that you have 16 terawatt of energy consumption, power units per unit, power joules per second, so we're burning a 16 trillion watt light bulb. That was my calculation by just taking GDPs and adding up the world energy use. That number actually comes out pretty accurately compared to what I just showed you. I can then go to the future and say, let's just make a rough estimate. On average, the world economy GDP increases around 2.3%. I'm going to have 10 billion people, and I have to make an estimate of energy intensity, which is conservation, right? If I can get to the same GDP and use less energy, I conserve, and I can quantitate that with energy intensity. So when you work that out, I'm going to contend you need basically 16 more by 2050. But in that energy calculation, I assume that you would save every bit of energy you're using today. So I did an energy intensity assumption that the world by 2050 will be saving 16 terawatts equivalents of energy, and you're going to still need 16 more. And that's because, and this is what I was trying to say, that's all being driven in the developing world. So you have low energy use to no energy use, more or less of 3 billion people when you finally add it all up. And most of the population increases in that part of the world. So when that part of the world starts coming online, you start driving this number here, and all the science and technology basically ignores this part of the world. And the second thing, which I'm going to stress today, is you can't sit here and say, I'm going to do something in this world, and oh, by the way, I'll translate it to the developing world. I actually think they're totally two different problems. At least when I do research, it's two different problems. So for the legacy world, and legacy, I mean they've inherited an energy system, which is most of the westernized world. That's centralized with this existing infrastructure of $8 trillion. So if I'm going to affect energy use immediately in this world, whether I like it or not, I'm going to have to do something that fits the centralized existing infrastructure. So how can I add something to that infrastructure to drive renewables? That's a different problem in the non-legacy world because there's not a big existing infrastructure. Thank God it's not centralized. If you were ever to rebuild it, why would you want to centralize it? And so therefore, this one becomes a low CapEx. There's not a lot of money for high capital expenditure.
Why don't we want to centralize one?
I'll get to it in a minute. But here's I like the sun. That's one of my biases. The sun follows you around everywhere. So one of the first things the sun gives you as an energy supply is a distributed energy supply. So I don't want, from a research point of view, to try to harness it and make it centralized, in my opinion. Then the second thing is,
Sun as opposed to?
yeah, I'll do wind too.
Yeah.
But I really like sun. I always say the reason I don't like wind is if you can put your hand this easily through your energy supply, you should look elsewhere, but that's a different issue. If you have it, you should use it. I mean, that's for sure. But the other thing about centralized is you got to build you got to then build a distribution. And I'm always with these EE people, electrical engineers, who are just silicon people, and they want to build high voltage grids all through Africa. And they can, but when you start looking at the cost of that grid expenditure, I'm going to argue I can actually go cheaper in a distributed with some really good discovery. That's one argument I'll make. But the real reason is the sun is following you around, and the poor, once you go centralized, you start accruing wealth, and if you're poor, you got to deal with it. So can I give the poor something where they can just take advantage of the sun and dirty water to get an energy supply? That's how I was thinking for doing my science. So one thing I want to do is, I put this in because I was talking to some of the students today, postdocs, at lunch, about what scientists do. And so this is what scientists do. And what I did, so what did I just do to say you need 16 terawatts in the future? We're sitting here, I said there's going to be this many people, and I extrapolated. I just did simple math, and I extrapolated. So what you do when you're looking out to the future, if you're policy or we sit here and we're going to be there, okay? And I just did it with energy. I said you're all worth some amount of energy. There's going to be 10 billion of you, and when I do my little calculation, I extrapolate forward and get 16 terawatts. I don't know if you guys have ever seen this. This is like a great extrapolation problem. In 1898, delegates from all over the world gathered in New York City. And this was like one of the first civil engineering conferences. Cities were starting in the US, they were becoming heavily populated. And you would say one topic dominated discussion. It was not housing, land use, economic development, infrastructure. It was, they were driven to desperation by horse manure. And what they did is what I just did in energy. They said, these are rich people, and they own horses. These are poor people, they don't own horses, but our economies are developing. Someday, they're all going to own horses. They assign so many horses per family, and you know how much dew comes out of a horse. And when they did the calculation, just like I did with energy, this is true, by the way. This is Eric Morris from UCLA. He's a transportation guy. The situation was dire. In London, every street would be 9 feet deep in horse manure by 1950. And then one New York prognosticator said that it would be to the third-story window of every building in New York, because they did exactly what I just did with energy. Now, you never heard of this problem, because then the internal combustion engine was developed. By the way, it was already developed. Just nobody knew about it. I like that piece. So I'm going to claim there's a lot of great energy that's been developed, but nobody knows about it. And what happened here, that's what we call paradigm shifts. So all of a sudden, it was ridiculous to do this, because that's what you're supposed to do in science, is discover something and make a whole new starting point. So the best thing I can do, it always makes me happy if I can do it, is when I was at MIT, I would sit there on this and listen to all these people, and it was with the assumption that the world will never change. And if you're a scientist, this makes you feel really happy because you make a discovery and the whole world changes. And that's what a paradigm shift is. This also proves to you that shift happens. You like that one, Steve? I worked hard for that. So today I'm going to tell you a little bit of shift happening in my group. Now I get to say that for the rest of the talk, and you know what I mean. So shift happening. All right, so Michael mentioned the solar study, and this is a report that it starts to, for me, tell you all the problems and how confused we are with energy. So the first thing is, I love this, we focus on for solar generation. It's a total solar generation issue. And I'm going to say right now that I don't even think that's a problem. Right? So we don't have a lot of solar, and the price has been coming down due to China and all these other externalities that you're all familiar with. And I remember less than probably 15 years ago when I was at MIT, we would talk about solar being $4 peak watt. And someday, if it got to $1, I remembered sitting in the room having these discussions, the whole world is going to change. That was the argument 15 years ago. I remember it like crystal clear. And now, guess what? We're under $1, and the world hasn't changed. And so my argument is, this is also for wind. It's not about generation anymore. It's all about storage. So that's my first bias. I told you, I'm telling you my biases. And so if you have good storage, my argument is you'll be able to penetrate markets with renewable much, 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 much more quickly. And so all of the research I'll talk about today is only about storage. So that's number one. And these are different consulting firms, and you know, the numbers come out pretty consistent across the board of a $500 billion market within the next 6 to 7 years. By 2030, people are predicting $1 trillion market drive in energy storage, and that's the whole thing. That's batteries in cars, it's grid storage, you name it. So the other reason why I think this is all important, storage, is when you have that sort of market driver, it's going to be around here to stay. I don't see that market driver in generation. And there's a lot of failed companies now with China sort of controlling the silicon market. So that's, in my field, there's a thing called perovskites. This is the new magic material. You can hit 20% solar efficiencies. That company, when a company started and they were going to displace silicon, they are now down to, maybe if we put a little thin coating of a perovskite on silicon, we can up the efficiency by 0.5%, and maybe there's a market there. That's all happened in 3 years. And so I think silicon is so dominating, I just want to take it off the table and only talk about this issue of storage. And that market drive is all due to storage, and there's nothing to do with generation. And so storage is two different problems. It's this world, and then there's the developed world. And in this world, it's what are you going to do to store energy? So here's a model, and actually this would be, I'm going to say this with no data, but it was my dealings with the thing I'm about to show you with the power companies. And that was when I talked to the power companies, if they could store energy at massive scale, energy becomes a commodity that's predictable for them. Right now they do load shifting. You can't have a reliable business model on load shifting. But once you're storing a bunch of energy, I know how much I bought back from you. You can send it over the wires in the ground. I'll store it and I can send it back to you. And I can set up a business model. I can even do things, and some of the power companies talk to me about this. If you get me this much storage, no, Sarah, I'll put the solar panels on the roof for these people because they're generating energy for me. I'll subsidize it for them. And of course, oh, by the way, in the sellback costs, I'll make sure I recover over 15 years from now. So you can start to see the power of our existing infrastructure in terms of getting renewable penetration if power companies can store that renewable. And so that's the problem we set out to do. And we made a thing called a flow battery. And I just want to tell you what a flow battery is. It's not like a battery in your computer. You take a glass of, so when you do a battery, you put electrons onto something and you take the electrons off. So lithium ion battery, you're actually taking the electrons out of lithium metal and then you're putting them in manganese, cobalt, or manganese, cobalt, or nickel oxide. So the lithium comes out here, it becomes an ion, the electron goes into the oxide and the lithium intercalates into the oxide. That's a lithium ion battery. In this battery, what you do is you take 2 glasses of water, and then I make a compound and I put the 2 compounds in there. And then when I take an electron out of the compound in this water, and I put the electron in the compound in this glass of water. It's just like a battery, except it's water-based battery. And the compounds are in the water. And so when the sun is out during the day, the resting state, or the low energy state, is with the electron on this compound. When the sun is out, I can drive the circuit backwards and drive the electron to the other compound, the high energy state. And now it's just sitting there in 2 glasses of water. At night, once the sun goes down, I can collect the electricity again because I can flow one compound by the other, take the electron out, and then in solution I have an ion charge balancing like sodium or potassium. And so it's exactly like a regular battery, except it's big tanks of water with compound in it. There's another huge advantage of a flow battery versus a regular battery for a power company. What this does is it decouples power density from electron density. So if I want to get more power, all I have to do, if this is my current collector, I just put more stacks of current collectors in there. And I could flow faster. That gives me more energy per unit time. Say I'm a power company and all of a sudden a new development opens up over there. I need more energy. All I have to do is build a bigger tank and put more compound in it. So the reason why power companies like flow batteries versus things like lithium-ion batteries, and there's a lot of lithium-ion batteries that companies that are going, because they can't decouple power density from energy density, okay? So this type of battery is very, very interesting to them. What I did is I invented in the company, Sun Catalytics, I started these two compounds, and it redid how people do flow batteries. They're called coordination chemistry flow batteries. I won't go into it. But the magic powder that goes into solution, we redid from the ground up. There are a whole bunch of problems with flow batteries. There were a lot of flow battery companies, and what they did is the typical thing you do, bad chemistry, bad science, but we'll engineer the hell around it. And that starts driving the cost of the battery up. For grid operators, you want to come in for a CapEx cost of around $300 per kilowatt hour for break even. So they won't entertain any battery technology that's over 300. Now you start realizing why lithium ion's been having problems at 600. If they say, know why they say 150? They have no idea if they're going to get to 150. There are even materials limited to get to 150. They're saying 150 because they know that's very marketable for a power company. And if I can fool you guys to think I can get to 150, I can get investment dollars to build my gigafactory. That's what's going on there, in case you haven't figured it out. So you really want to come in at around below 300. And the further you are below 300, the better it is for the power company and the more valuable the battery is. And then you can do grid storage. I do want to say you could go to the developed world with microgrids. In the battery I'm about to show you, we actually made it a 10 kilowatt hour prototype that would have fit perfectly into a microgrid. So what do? You have a discovery. Guess what my discovery was? It wasn't the flow battery. It was making hydrogen from the artificial leaf. I'm going to get to more about that later. So you start a company, lots of hype. Nocera has made the artificial leaf to take sunlight to split water to hydrogen and oxygen. I'll explain later why that was important. And so you start a company. So I'm a founder. You go steal the CTO of United Technology Corporation. You get some general counsel. Everybody thought the oil companies were going to kill me, so you get the ex-director of the CIA to protect you and run your scientific advisory board. And then so here's the first smart thing I did, and it was smart because I had him as my friend, is you go get very accomplished business people because scientists don't know how to run companies. So Art built this company called Ionics, and he sold that to just the largest water desalination company in the world. He sold it to GE Ionics now. That's what it's marketed under. Metcalfe founded 3Com. He invented the LAN protocol. He's the inventor of Ethernet, not internet, Ethernet. So you get Metcalfe, and then we all wanted nice cars. So we got the CEO of Jaguar Land Rover. I'll tell you why he showed up in a minute. And then we started the company. So I'm going to show you, we were on a path that you use in America, and I realized we were going to fail. And I'm going to show you how we were going to fail. So first you get a $2 million VC round from Polaris. Then we got an ARPA-E grant. The ARPA-E program from DOE was crucial because that gave us $4 million after the $2 million in Series A round. And that was able to allow me to put a company together, like to get a CTO and stuff. So ARPA-E actually was incredibly important, and that's a very good DOE program. I'm a big proponent of that. And then what we were is now you're going to go Series B, and everybody starts talking about return on investment because now the money's starting to ramp up. And remember, I'm making hydrogen. There's no infrastructure for hydrogen. So what is the ROI on, I can give you hydrogen renewably from water, and by the way, I don't know what you're going to do with it. So you can start to see the problem. And so first, what's an ROI on a renewable hydrogen-based? There's none. Because there's no infrastructure. And so we adapted quickly, and the how we adapted is we went to grid storage. And everything I'm going to tell you about water splitting, which will come later on in the talk, which we developed and worked beautifully, you basically want to have inverse design, the worst water splitter in the world. Because remember, I'm putting current in water. If the current went into splitting water to hydrogen and oxygen, I would lose all my battery storage capacity. So in a funny way, what we had to do was inverse the artificial leaf and prevent water splitting. And that allowed us to, so we were so good at water splitting, we just had to be the worst water splitters in the world and then make 2 new compounds. That's what we did. And it worked beautifully. So we had all these constraints, and then thank God Mr. Todd showed up and he funded the company for Series B. Because we weren't going anywhere with VCs. VC models don't work for energy. So this is what I'm telling you, in a solar fuel, it's this idea of coupling protons and electrons. Electrons are quantum mechanical, protons aren't so quantum mechanical, they're more classical. It's hard to have couple electrons to protons. It's called proton coupled electron transfer. To split water, you have to do that really well. So here you want to do it really off, you want to be really bad at it. That gives you a high over potential. That means I have a big window or a big voltage to store water. So water gets split thermodynamically at 1.2 volts. So if I make a good water splitting catalyst, I'll only have a 1.2 volt window. To operate, I would be at 0.9 volts. The battery we developed was 1.65, 1.7 volts because we did this inverse design. And I won't go into it, but we had to develop this chemistry, and we developed it from the ground up to take out all the problems of flow batteries. And I'll just tell you, it worked well. In the Series B, we built a 10 kilowatt hour prototype. And so we built the prototype at Sun Catalytics, and then you go to Series C. So this is what you would normally do, right? Now I have a prototype, it's working. We estimated this thing at scale up would be around $225 per kilowatt hour. Remember, 300 is the magic line. We had people come in and use it. We let our potential investors use it. That means they had to be in the business. So the first thing we didn't do is just go look for money from an investor. We wanted somebody who said if they invest it, they might use it. So we had people using our prototype. And then you start thinking, I'm going to get 35 million. That's a good Series C round in this field. And guess what? I was at an 8 million a year burn rate for 30 people. So you're talking 4 to 5 years. Now remember, the world's moving fast, and I'm going to be trying to develop this with 30 people over 5 years. And that's where you enter the valley of death, they call it, meaning you never come out the other side, because while you're messing around at $8 million a year, there are massive corporations in the business of energy storage because there's a $1 trillion market. And I have my 30 ragtag team of people, very smart. So I started worrying about this whole Series C investment and the typical investment strategy. Now, How does it work? These guys, like VCs, remember, it works for IT because it's low CapEx. Give a kid a computer, put them in a room, maybe they'll come up with something. So that's easy. So you're willing to invest if you're an investor. There's the potential of a high ROI with low capital expenditure. The other place it works in academics is pharma. But remember, in pharma, that can be expensive when you have to go through these drug trials. But in pharma, you sell hope. I made the magic pill to cure cancer. You guys will pay anything for that. Energy, you don't have hope, and it's not low CapEx. You know you have energy, right? So this model starts totally deteriorating. And I was sitting there through 2011 thinking, 12, I do not want to take this investment model. I want an early partner. And then, like this article came out. Actually, this is a great article. It came out 8/21/2014 in Forbes. And it said the MIT curse strikes again. Lilliputian Systems runs out of gas. And it talks about how wonderful MIT is. It's an academic beacon, but sometimes startups just aren't its bag. This is almost like this is like going against the Church of England, right? Or the Pope saying MIT startups aren't its bag. So first thing that he did that's wrong, he meant to say energy startups aren't its bag. So that's the first thing. And then you start going through, this is what I'm giving you the short version of the article, 140 million, dead, bankrupt, 30 to 50, dead, bankrupt, 200 million without even the low interest loan from DOE, bankrupt. So every one of these countries are bankrupt. In my field, in academics, these are all success stories. You got to Series C and you got this. To investment bankers who really are driving these market, failure. So there was this disconnect, and it's exactly the one I'm telling you. I'm going to get Series C. I'm looking at all this stuff thinking I'm going to get some Series C funding so I can keep increasing the value of the company someday, so we can all make money. And
So you think, go back to like, all those companies had socially valuable technologies, but there was something...
yeah, they're taking too long to go to market. The energy is a very capital intensive thing that you're trying to go against a very established infrastructure. And I just don't think you can do it in a startup VC 30-person mode. I just think it's untenable because of the CapEx and established energy infrastructure.
So presumably somebody owns the intellectual property for all these
Yeah.
startups, and are those big companies that are taking these technologies?
Like a lot of these things, the energy, so first off, like this might work, but it's not going to work now. So you don't even want it because you're looking for an ROI in 4 years from now, right?
And so the typical thing we would say now as well, but look at pharmaceutical companies
Hope,
and say, they make investments for 10 or 12 years, and your reply to that is
hope. If they didn't have hope in the magic pill, which people will, and the government will pay for hope, and investors will pay for hope, if that didn't exist, it would not. If there's nobody doing a 10-year investment in energy that I've met. If you find an investor like that, please send them my way.
But so another way of sort of classifying IT and then pharma is that IT is low capex and pharma is hope. Isn't that sort of just saying that energy is both high capex and low margins once you sort of get there?
And no hope. I mean, there's,
But hope just sort of means that the possibility of effectively enormous margins. And you're talking about that because we're talking about energy. And
yeah, the margin is, yeah, that's right.
margins are small.
Yeah.
So the people in the intellectual capital are bought off by big companies?
For the intellectual capital.
Yeah.
Yeah, but my argument is these guys, to get to a competitive point for buy-off, they never come out of, they're dead before that ever happens. They're moving too slowly.
But you're also trying to make a significant change in the biggest inertial system.
Right. And so by the time, that could happen, but by the time you can get to that, moving that inertial change, to start that inertia, there are all these other competing technologies, markets have changed, and I think that's why all these companies fail.
How do you lump luminous devices into that?
Yeah, that was like a lighting issue. That one just got beat out. That was a perfect one. I think this guy got beat out by the mega companies like Samsung. And so again, this actually is this is closer to what I'm going to say. You have major corporations in lighting. You have some great technology, you think in lighting, but you have all the distribution issues and market issues to finally be competitive. And they ended up losing just because there were mega companies in the LED space that could just swamp them at the end of the day. So,
Yeah, but should we, like, I'm sure you're friends with the guy who did Luminous, but should we be concerned?
in terms of,
I mean, we should be concerned for him personally, but societally, should we be concerned?
no, except that there may be some promising things here that just aren't getting to market quick enough and just are dying off
When you
because.
say quick enough, I mean, that means something else is being, if the established guys are keeping new technology from ever entering, now I'm concerned.
Yeah.
If it's just that these things take a long time, something better comes along in the meantime,
Yeah, that's right. There's no problem with me. But except that what's something better in the meantime for like some of these things? Fracking. So I mean, so the something better is, so fracking came along, and maybe I would want to get one of these up and running to make it look and be market competitive, so there's a choice between fracking and something else, for instance.
okay, so this is in the absence of perfectly pricing carbon.
Yeah, look, if that happened, this whole story changes.
We don't have to talk about it.
Yep, I totally believe that. And once you start pricing carbon, everything I'm saying is out the window. Because there's actually an investment drive then for some of this stuff. And they will have patience under that. And if you price carbon, you know, the one nice thing is, like, you deal with this a lot more than I do, Mike, but when I talk to these people, they're not even worried about pricing carbon. They just want to know if it gets priced, it's going to be there and it's not going to change a long time, so they can actually make educated decisions. They're petrified with the pricing, then the price will start changing and they can't do anything with certainty over a 10-year investment. So when I talk to most of the big companies about carbon price, they just want a stable carbon price that they have to work against. And I think that would help a lot. But I'm assuming that's never going to happen in this world that I'm in right now. So what did I do? So this is what you usually do. You build a Series C. By the way, a lot of people, like the founders, made a lot of money here. Even because with this investment, there's a lot of money being changed and people are taking money off the side. And that's the problem with academics, is what I should have done is taken the 35 million, keep increasing the value and hype of the company, and to be perfectly honest, sell it at some point to somebody who's not in the game because they think they have something valuable and it dies. So if I were smart, what I would have done, and this did happen, I would have held this company, increased its value, and sold it to a Silicon Chinese supplier, because that would make their thing more valuable and they would pay for it. That's what I should have done if I wanted to shove money in my pockets. So I should have done that. And then been like that. It would have died because I would have had the technology actually in the wrong hands, a silicon manufacturer. I needed to have it in the hands of an engineer. So the model I decided on was to find a super early partner who was going to come in at Series C and say, I don't want your 20 or 10 million, I want 250 million, and we need to do it now. And so that's what we did. And now that's going to go into the hands of somebody who can really drive the technology hard and fast. And so Lockheed Martin, we tied up. And the reason I told you, look at that article, that MIT Forbes article. It was written on August 21st. And he ended the article saying, Oh, and by the way, the next company to fail will be Sun Catalytics, and he wrote that on August 21st. Of course, I knew this was all happening. And August 25th, they bought all the assets of Sun Catalytics. In a deal I can't divulge, but it was very attractive for them. I undervalued the company a lot because I had the most shares, so I could decide on how to undervalue it and then control what they're going to do with this. And the nicest thing is, when they bought this company, they announced on Wall Street that this is a defense contractor, that they were now an energy storage company as well, that was going to go to market with an energy storage device. So this is part of Lockheed Martin's business model now for future growth, which is really important. So that happened. We have this thing, which was running really nicely. They used it, and all the metrics we provided them, they actually came in cheaper. They said, you're way over $225. My hope is, right now, this battery is going to come in at around $175 per kilowatt hour. So as I speak right now, these guys are going to they're designing a very, very, very large grid storage battery based off of this system. And so this early partnership model, I feel really excited about. But there's one thing is professors aren't going to become rich off of it. Because and I don't think we should. So I really despise, I'm starting to hate my community, where a professor makes a discovery and they think they're going to become wealthy. That might happen with IT and pharma, but it's not going to happen in an energy capital-intensive market with an established infrastructure. So I really think the biggest problem with translating technology is starting with the inventors and academics. And it's partly being driven by the universities who think that they're going to make a lot of money off of these inventions, and they never make any money. And so who should make the money? The people who should make the money are the people assuming the risk. And the people assuming risk here is Lockheed Martin, off of my little prototype, okay? So I think that's really the problem with right now moving discovery to market in this field. And we'll see, but I believe, remember, we developed this chemistry on the bench was developed in 2011. So this 20 to 30 year time horizon, I think, is totally self-imposed by people who want to, they're putting greed over vision. It's that simple. And I know I'm at the University of Chicago. I'm certainly at Harvard Business School. Oh no, if it's valuable, you should, everybody's going to become rich because it's valuable. And that's true. It just shouldn't be me as founder. It should be Lockheed Martin, in my opinion. So I basically gave them everything for free, more or less. The price isn't out there, but it was very, very attractive for them to take this company.
So your argument is that
Get an early partner and let them become rich off of it. You should be
sell it for too little.
sell it for way too little, and make it good. So this is what I say: use investor money to build prototypes that partners who will drive the technology use, not investors, and let them kick the tires. And then if they like it, and this took over 8 months with them using it, when they really liked it, we said, you take it now and please, drive the technology. And they want to because they look at this as something that could be extremely profitable for their bottom line in the future.
So how did your early investors feel about it?
They got paid off. And so the VC just wanted out. Guess what the VC's doing? Holy cripes, 220 million. We're going to be so diluted. It was to their benefit to get out early because of the dilution issue here is amazing as you start moving it.
So knowing that this is like the plan that you have for this particular business, when you go and do another business like that, do you think it's going to be harder to raise money the next time around, or will it be easier to raise?
No, I think what should happen now in like universities with energy initiatives, they should be setting up a total early partnership model, not these VC investing, get a company, let's make a lot of money for the university.
But the responsibility for breaking into the energy market now falls to Lockheed Lockheed Martin.
Yep. And that's part of their business plan. And they announced it on Wall Street. They have a way bigger incentive to succeed now.
And
that is part
they're
of the
much
model
better
too,
at it
but-
than you are.
Oh, they're way better. This is a huge engineering project. I mean, there's no way I could pay for this. I don't know the numbers now, and I know I'm being filmed, so I don't want to give the numbers, but it's way over 30 engineers working on this problem at Lockheed Martin right now.
Why not as part of the model, having the universities keep a fraction of the profit?
Yeah, so that's why I'm here. You guys should figure out the way universities can be happy too. I was adult, I don't know economics, and I just wanted us to go fast. So the easiest thing for me was to give it away. Yeah.
But in the case of A123, I guess what you would argue is that rather than trying to go to manufacturing, they should have taken that technology and tried to get it in the hands of GM or whatever.
Yeah, let them do the manufacturing. Let them own it. That means it's way more important to them. And GM, remember, that was going to be their big customer, and then they pulled out. If they were owning it early, they would have been much more committed than finally going, and then as soon as they pulled out, A123 tanked. Now they're getting saved supposedly in China. We'll see how well that works.
In terms of this, do you have any comments about Tesla?
Yeah, Tesla, look, in terms of energy storage like this, it's going to fail. Because lithium-ion batteries will not be able to do grid storage. What Tesla's trying to do is get the battery price from 600 to 300 with manufacturing, and that's really important for the car industry. Oh, by the way, this you will not put on a car. The energy density is too low. So what he's trying to do is get the price to 300 because that takes the Tesla price and divides it by 2, which means a $90,000 car becomes 45, and that's a real market. So what he's done, though, this is my argument against what he's saying, is he's selling this as also grid storage, and I believe lithium-ion batteries will never get there, but he's trying to drive investors to help him build his gigafactory to get the price down for a car battery. And
Do you still have equity stake at all?
No.
Skin in the game whatsoever?
no. Why should I? Because it's a business now. It's their business. I mean, they hire me on retainer when I have problems, like if they want my advice for chemistry. But when am I going to help them with engineering?
Do you feel as though you've been properly compensated for the discovery?
No. You mean financially?
Yes.
No. What's my compensation? My compensation is something I invented that I believe could actually really start moving renewables to market. I did. That's what professors should do, in my opinion. We shouldn't be here making money. If I want to do that, I shouldn't be a professor. So my compensation is I invented something that I listened to Harvard Business School tells me you will never get, it's going to take 30 years to go to market. Green investing is done. It's not going to work, and I'm going to show them wrong, so that makes me feel happy. And I'm going to go to market quickly, and I actually believe what I'm saying. If the power companies have this level of storage, that's going to accelerate you guys having solar panels on your roof because you'll be using that $8 billion infrastructure to just shuttle energy, and you'll be an energy generator. So once you have this much, a lot of energy storage at a power company, I believe that's the quickest road for wind and solar penetration into the market.
Are you totally intellectually divested as well? They no longer need your services?
They will, there's things I know we could do to make this battery better in energy dense. So I might go and return to this someday, but I have bigger problems right now. I'll show you in a minute that I decided. I only have a group of 30 doing work, so I decided to go a different route. I have a whole bunch of good ideas to make this better. So then let's go back to the solar study. It makes it look like I'm picking on MIT. I'm not. It's just, I was on the solar study, and the next thing this is all in the executive summary. This is a typical thing we do in this world. Progress will contribute to greenhouse gas reduction. It's going to help everybody else that's in the developed world, and by the way, we're going to help 1 billion people without access to electricity. So that, I believe, is all BS. And what I'm going to do is show you, this is a word which now you can see I moved to Harvard because I learned words like this in philosophical thoughts called solipsism. Solipsism is like worse than self-indulgence. Solipsism is that you people exist, you don't actually exist. You only exist because in my mind I've allowed you to exist, but you actually don't exist. That's a philosophical thought of the whole world existence only is there because in my mind I've allowed it to exist. It's way worse than being self-indulgent or being narrow in your view. So the idea that only one's mind is sure to exist and therefore allows existence, that's solipsism. And any experience I have is only because I've allowed it to be in my mind. And that's how we do energy. That's what that statement is saying. Because that means self, and the world I live in is the one that exists, and that's 3 billion people. And my argument is those 6 billion, we don't see them, so they don't exist as far as energy is concerned. It's that simple. Yeah?
I am wondering how all this technology that you're proposing is going to be a death knell to the nuclear.
Oh, to nuclear?
Yes.
You know, people can do nuclear. This is my argument. Nuclear is a large CapEx investment. So I don't even see it going into the developed world quickly. And forget this country. Like, we could do calculations. A nuclear power plant puts out roughly a gig a watt. If you want 8 terawatts, you need around 8,000 nuclear power plants. And you know, you like to decommission after 50 years, even though they try to extend them. And so just to maintain that amount of nuclear power, you're going to be constantly building nuclear power plants, and it's hard to build a few. And that's a big capital expenditure. I'm going to get to that in a minute. So I'm not really worried. I don't think about that for
Well,
this.
I think this is a,
Yeah,
make that other, the nuclear potential obsolete.
maybe. We'll see. I mean, these are good discoveries, but we'll see if they actually go to market. So I'm really focused. I told Michael I came here. I'm really focused on how do I translate discovery to market. That's what I'm really starting. So this was my first attempt, was to do this different early partnership with a partner who has skin in the game. So that we just talked about. I'm going to argue for the developing world we should do decentralized energy. That was Michael's first question, and it's because the sun actually does follow you around. You could use batteries, but I just want to remind everybody the limit of a lithium-ion battery is 2 megajoules per kilogram, meaning how much energy you can store. Gasoline is 45, so that's 45 to 50. It's 100 times that of a lithium-ion battery. That's why when you get in a Tesla, you're getting into a large battery pack. And that's replacing that thing that's this big in the back of your engine. That's energy density. And at the turn of the century, you could have gone batteries or you could have gone fuels, and guess what you chose? Fuels, because you intrinsically understood this number. And that's not going away, and this is like theoretical limits. I can't put any more electrons in a lithium-ion battery. So right now, you're at half. If you were to get to 2, this is a practical theoretical limit. If you get to 2, it's a factor of 4. That does not solve 16 terawatt storage problem for the poor. But if you own a car company, going from 200 kilometers to 800 kilometers is a big deal. So I just want to bring this up because people confuse the battery thing with massive energy storage for the poor. They're 2 different things.
Whenever I see a chart like this, one thing I wonder is about conversion. And so, like, there's just some research
Yeah.
off Marmon this week and talking about the conversion efficiency.
Yeah.
Now, when you're looking at vehicles, at least, you should look at
80% conversion. So now you're going to get 80% out of a battery if they could do deep cycle, which they can't. But a fuel cell is 60, an internal combustion is 30, and if you go to mechanical systems like flywheels, 90 Carnot efficiencies. So you're like 80 versus 60. So that's important from a money-making point of view. It's important for cars, but if you go from 60 to 80, we're not talking about 16 terawatts of storage. That's all in the noise again. So I just want to bring, I think for large-scale storage, especially in the poor parts of the world, and this is why all these lithium-ion batteries are failing when they try to say, we're going to do grid storage, by the way. It's that simple. So how can you do decentralized solar? And what I said is you want to have CapEx and distributed. And I'm going to now say something.
Do you think that's going to be able to beat centralized natural gas or coal at the end of the day?
Centralized natural gas or coal. Yeah, you got to, so that's why I like this.
And I guess
That's why I like what Elizabeth's doing. You got to go build that, and you're going to have a cost. Is there a better path that's going to be cheaper, that's decentralized? So that's why I want Elizabeth to please publish her paper, because she's been studying this to say what is the, because that's what you're going to have to do in that part of the world. And the question is, could we get there faster with some alternative for less than 8 trillion? So just see what I've done, and you can decide if there's
I
any.
think you also must be thinking that they don't, in many parts of the world, there's no guarantee of 24/7, 99.9999% reliability. And so that is also.
Well, that will happen, but a long time that will take.
But it's helpful today that it's not.
Right, yeah. Like when I'm in India giving a talk, have you been there? Even just like in Mumbai, the lights will go out and nobody moves. They just wait, and then 2 minutes later it comes back on and you just keep on going with your presentation. Like the first time it happened, I was, oh my God, my talk's over, and like nobody did anything. They didn't get up, they just sat there. Then the lights came back on. So reliability in India is a huge deal, even with the grid. If you can retrofit the grid, people will, that's very valuable to an emerging grid in India. So I'm going to argue low CapEx and distributed, and I'm going to now say what this translates from a science point of view, lightweight and highly manufacturable. So what do I mean by that? So what I did here is wait, I just want to make sure. Okay. So I plotted, look at what I did. I took the cost in poundage, that's it, nothing else. I didn't care about any details. So I went on the web and said, how much does a Boeing 777 weigh? And I normalized the cost with weight, and how many did you make? And I did it for all these things. And so what's happening here? What doesn't this work for? Intel chips. That costs us a lot of Intel chips. It doesn't work for pills, pharma, and it doesn't work for commodity. But for stuff you make, just like manufacture, you can never get cheaper than $10 per pound. It's Darwinism of material science. And people don't understand when they do material science, they're trying to just beat $10 per pound. And what's $10 per pound? That's basically the price of copper, cement. Like when you build large plants, that's what it comes out to. It's $10 per pound. And it works for things that you make a lot. This is honest to God truth. I literally called this. By the way, first I didn't know McDonald's had a CTO. They have a chief technology officer. And the price, if you just take the weight of the patty, the cheese, the tomato, and the bun, it's $10 per pound. I'm not kidding you.
Well, what about the building?
And the only thing I should do here is I should have a squiggle and have infinity for number manufactured. It's way over 100 million a year. I just kind of put it out there. So even a hamburger is not that different than an automobile. And you'll be surprised, in your automobile, outside of the Intel chips, it's mostly the weight of the vehicle you're paying for. It's unbelievable. Okay, so what do we do? This gets back to your question. When we do energy systems in the legacy world, at $10 per pound, we build one heavy thing. I need a CapEx. And then I got to set up a market model that I recover my CapEx. That's what's been stopping penetration, I think, in the developing world, thank God. And so I literally, this is no lie, if that isn't going to work, we, a few years ago, set out to say, could we make a McDonald's hamburger of energy? The other way to say this, if McDonald's had the business model of our centralized energy system, what would McDonald's look like? You would make one huge hamburger, everybody would drive to it, take a bite out of it, and go back home. Just think about it. That's literally how McDonald's would operate. So if that business model isn't going to work, could I build a different business model, and therefore could I make a hamburger that I could hand out to everybody? The sun is following you around, and I'm going to use the hamburger to convert sunlight into energy. And that is done. What is the hamburger of energy systems? It's leaves on trees, because that's what leaves do. They're highly distributed, and what they do is they take sunlight plus water and they make oxygen and hydrogen. They split water to oxygen and hydrogen. Then at night, you think about when you were in school, if you took a science class in high school, sunlight plus water plus CO2 makes oxygen and carbohydrate. But what people forget is the H2 plus CO2 is a dark reaction. There's no energy storage. Nature did that because it didn't know how to deal with gas. Hydrogen is a gas, so it stored hydrogen in a solid form. That's what biomass is. I just want you to realize that. All the energy storage in photosynthesis is in water splitting. So here's a fuel right here. And so what you have here is high energy bonds, gasoline plus O2 makes CO2 and water. And what happened in photosynthesis is you took all that biomass, it ran this reaction backwards with sunlight, buried it under the ground, and you're taking it out at around 1 million years of photosynthesis per year now. You guys are letting into the atmosphere. So it took 1 million years of photosynthesis to do and put in the ground you're burning per year now. That's about the what we're doing and releasing all that CO2. So what's photosynthesis doing? It's taking these low energy bonds of water, and this is where all the energy storage is, to make H2 plus O2. So you're storing sunlight in the rearranged bonds of oxygen and hydrogen. Okay? Let me do a little calculation for you. I like doing these like calculations just to get, see, I knew that I was going to upset somebody with this talk. So if you take hydrogen, and I said I could take some amount of water per second, and I'm going to convert it. So I have a hamburger, and I'm going to operate on an amount of water per second globally. How much energy could I store? So in 1 mole of water, 1 unit of water, I can store 13 megajoules. So what does that mean? If I take the Harvard swimming pool, the hardest thing with this calculation is finding out it had 2.8 million liters of water. That took forever. If I could build an energy system, a hamburger, and globally, per second, we were operating on a pool of water. By the way, that's 10 times the amount of nitrogen and ammonia we're dealing with Haber-Bosch. So I'm going to take a pool of water per second. Now, you're not using it up, right? Because when I split water to hydrogen and oxygen, when it recombines, you get the water back and you release the sun's energy, but in a useful form. So you're not using it up. You're just cycling through a pool of water per second globally. If I do that, 38 terawatts. Now, that's at 100% efficiency. So say we have a 60% system, like a fuel cell, then it's 24 terawatts of water. So we started wondering, could we have a hamburger that could take sunlight plus water, and I would need to operate on a pool of water. I could get you 24 terawatts. You only need 16 renewably. So that at least sets a problem for research. That sounds like a good problem to work on. If you do something there, it could be interesting. That means I have to emulate photosynthesis. I will tell you, people have been doing it, have been talking about this for over 120 years. So here's a paper in Science in 1912 from Chimichan, who said if our black nervous civilization based on coal and oil shall be followed by a quieter one, that wouldn't be harmful to human progress and happiness. And believe it, in 1912 he said, could we fix solar energy through the photochemical reactions with new compounds that master the photochemical processes? Has been the guarded secret of plants. This is an amazing article if you ever want to read it. In it, he talks about could we inoculate plants to make products they don't make. That was basically bioengineering. He talked about clothes that would change color when sunlight would hit them. photochromic. I mean, it's an unbelievable article. He talked about photovoltaic materials, being able to take sunlight and make electricity with the material. And then one of the other things he said, could we emulate photosynthesis? So how does photosynthesis work? Sunlight comes into the plant. Plant can't get its hands around it. So what it does is it immediately changes sunlight into current, moving charge. And that's what's happening in the membrane. So sunlight comes in, and you immediately get a negative charge moving one direction and a positive charge moving in another, and that's current. So when you look at leaves, they're buzzing with electricity, just no wires. Isn't that interesting? Then the plant knew batteries aren't good, because that charge is in cofactors, and you just take a metal, and every time an electron in a hole, you just up the charge. But the plant knew that was too low in energy density, this energy density. So what it does is it then, after 4 units of charge from sunlight is accumulated in the cofactors, it takes the stored battery charge and it operates on water, which is a 4-electron, 4-proton reaction to make O2 and hydrogen. So that's what it's doing. So it's sunlight in, energized wireless current, and then you have catalysts, cofactors, that take the store the charge and then operate on water to make oxygen and hydrogen. So we said, could we build something like, can I take silicon, because silicon does that. When you put sunlight on silicon, you get a wireless current, then you put wires on the end to collect it. But could I take the wireless current and direct one side of the current to one catalyst, I'll coat on the top side, another catalyst on the bottom side, and split water to oxygen and hydrogen. And then there's this dark reaction, the hydrogen problem. So I'm not going to tell you any of the details, but this guy in 2008 at MIT discovered that catalyst which self-assembles, and that splits water to oxygen. It does half of this. This is the hard part, is to take 2 oxygens from water to get them to come together to make O2. Then the protons are hanging around. You can make hydrogen later on. So that compound worked, but the important part was the first self-healing catalyst. So this just shows, like, this is the catalyst. It's breaking down, and then it fixes itself, breaks down and fixes itself. So that was a fundamental science problem. We figured out how you could make a catalyst and have it heal itself. Now, why is that important? Because if you take, this is an oxide, and you put it in water, they corrode. And that's the corrosion problem. It's been known for over 100 years. So what we did is we designed chemistry, which I'm not going to tell you, where on the fly the thing was always fixing itself and healing. That means I can use water. I don't need concentrated base or acid, simple engineering, remember. The other thing is I can have this operate out of seawater, the Boston Harbor, Charles River, urine. So why is that all important? If you're in the developing world and I got to ship in 18 mega-ohm pure water, forget it. So that's why we were hell-bent on making a self-healing catalyst that you could just take a puddle, or you could even take urine and split it to oxygen and hydrogen. Interestingly, which I've never had time to follow up on, when hydrogen and oxygen recombine, what you get? Clean drinking water. I haven't even had time to do that. I just wanted a catalyst that could work in any water source. So that was a science problem. And now if I'm in any water source, I can easily integrate it with devices because water is in a harsh environment. So the real key was to make this self-healing catalyst. And now I'm going to tell you, if it's in water, I can interface it with biology easily. So a few years ago, 3 years ago, this is the artificial leaf. These guys took 3 flavors of silicon. This is amorphous silicon, germanium in silicon, and more germanium in silicon. So silicon, amorphous silicon, has really tortured bonds and strained bonds. So amorphous silicon absorbs there. And then when you put germanium, it's bigger in the silicon, it relaxes the strain bonds. And depending on how much germanium I dope into this, I can hit that, and then I can move that to there. I put more germanium, I move it to there. Why did I want to do that? I take that plus that plus that. That perfectly overlays with the solar spectrum. So that's the first problem with photosynthesis. Photosynthesis can't perfectly collect the entire solar spectrum. It's green. It's only collecting a certain part of it. That puts a limit on photosynthesis of, first, sunlight coming into water and hydrogen. It operates at 28%. Then when I do the integration of the absorption profile relative to the solar profile, the theoretical maximum of photosynthesis is 10.2%. So that is the ceiling. You can never do better with a photosynthetic organism. Then it turns out to go to biomass, the fastest growing crops are 1% because it's using most of the energy to survive, all right? So if you listen to what I'm saying subtly is I just beat out photosynthesis because I can engineer with inorganic dead stuff an absorption and charge separation machine that's way more efficient than photosynthesis. And then I coated the cobalt catalyst on top and we put this nickel catalyst on bottom. And this thing literally works like this. You can watch it go all day. You just put it in the window. At 30 milliamps per centimeter squared, the sunlight is coming in. The positive charge is going to the top. It collects 4 times just like in a leaf. And then it splits water to oxygen and it bubbles off the front. The electrons are going to the back side. The catalyst on the back side is this nickel, molybdenum, zinc, and it makes hydrogen. I'm letting these mix, but usually you just put a separator and just collect the hydrogen off here and the oxygen in. Literally, the way I just told you, I wanted a hamburger. It's literally this one right here, wireless current. So I was thinking, what does wireless current? Silicon. Then you have cofactors. I need to make catalysts that collect the charge, but it needs to be self-healing. I literally am showing, I mean, I'm not, this is exactly was our thought process.
And did this come in like one moment or just?
No, I said, I got to tell you, I said this before to somebody. I started this at 24 years old. I said, someday I'm going to make something that you drop in water, and it's going to, I started at 24 years old. So what I'm not telling you, there was a field, this proton-coupled electron transfer wasn't invented. It took me 12 years of my life to do PCET. We did the first measurements. I developed a theory around it because I needed to couple the electrons and protons. I spent 10 years to do multi-electron. I gave myself all these benchmarks of 10 years to get the science right. And then when I had it all in
You were targeting that?
No, and then that was the surprise. I was targeting a compound that you would dissolve in a glass of water, and we did that in 2002. And then I realized compounds had the problem of the leaf, which is, where's my spectrum of the sun? Shoot, I lost it. My compound only absorbed a sliver, and then I said, I did this perfectly, and I can only be at 1%. And then I realized, God, I got to go use a material that I can engineer to cut. So it was just following that thought process. So
Notice in effect, although this is intended as a compliment, you're still thinking like an engineer.
I know. So that's systems engineering, reverse design systems engineering. Then you got to invent science. Okay, so it's a hamburger. That's the patty. There's the cheese, bun. It's simple engineering, just like, and this thing you can, what we're doing at Harvard now is I can make this all by chemical vapor deposition. As the thing is going by, we can spray chemicals. See, I don't need to wire it with engineers. It's just coating. It's just like a hamburger. So this is very adaptable to manufacturing. And we can hit 12.8% efficiency. Sunlight in to hydrogen and oxygen. Like not the PV efficiency. With a 15% solar cell, I can produce hydrogen and oxygen at 12.8%.
What's the typical thickness of the layers?
100 nanometers. 100 nanometers, 100 nanometers, 100 nanometers. It's 300 nanometers sandwich. And it can use any water source. So it's doing just what I told you. And you go, hooray, and that's what started the company. And everybody was excited by it. So what will you do with hydrogen? That's what you do with hydrogen. Like if I give you my renewable hydrogen, the only thing you'll do is blow up balloons with it. There's no infrastructure for hydrogen. That's when we made the shift to the flow battery. And we reverse designed all that science I just told you so that we could have a large voltage window. I wouldn't split water and I could put compounds in it. Okay, so what did we just do? I'm going to be like biology. I want to go the whole way. So I started getting hit like hydrogen, hydrogen, hydrogen. And so what could I do? I went and started a flow. But I really think this is the way to go. I have the fuel, but remember, H2 plus CO2 goes in the dark. I don't need sunlight anymore. So this is what we did. We took a bug. This is all in the last year and a half. I took a bacterium, and I have hydrogen. Because of genomics, we can genetically encode now by science. I can go into a bug and say, I'm going to give it a nose for hydrogen. It's going to breathe the hydrogen in. Remember, that's the high energy product. I can choose the hydrogen. I got to convert it into energy for nature, which is ATP. And then from there, I can put in different genes and think of the bug as a manufacturing plant, and I'll change the manufacturing depending on what gene I put in there. And then I'll put something on to make it excrete it, another gene. And that's called synthetic biology. Because we know so much about genes now, I can go into a bacteria and genetically encode stuff. So what did I just tell you? This is where photosynthesis fails because it doesn't absorb. This is the 10.2% piece. I just got rid of it with my artificial leaf. So if I can figure out a way for the bacteria to breathe in the hydrogen, I just offloaded all the inefficiency of photosynthesis. And that's what we did. We put a gene in, which is called hydrogenase, and hydrogenases take H2 to 2 protons and 2 electrons. And then we put a gene in, I'm not showing you it all, that takes the protons and electrons to NADPH. And when I'm at NADPH, I can convert to a thing called ATP, and ATP is the energy currency of biology. And this thing has a Calvin cycle in it, and it makes biomass. But right at that branch point, we said, I don't want to make biomass. I'm going to use the ATP, and we put 4 genes in it. Gene, 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 gene. What do those genes do? I like this. I'm showing it to you. This is just chemistry now. I needed to, this is acetyl-CoA. I need to couple that carbon to that carbon. I make that product. That's what that gene does. It's called that's what CTF does. It's called acetyl-acetyltransferase. Then there's an enzyme that will get rid of CO2. That leaves acetone. A decarb, I put that gene in. Then I need to hydrogenate it. Now I've made liquid fuel, isopropanol. So we did that. And we even went crazier. We made isobutanol, isopentanol. In one manifestation here, we put a gene in and it makes plastic. So I can make plastics this way. But right now we're making isobutanol, isopentanol. These are all alcohols that you could burn directly. And it's coming from hydrogen, from split water, from the solar, and it's breathing in CO2 from the atmosphere. That's what this bug's doing. And I'm showing you, this I think is going to make a big splash. I'm about to show you in a minute, but the proofs just came in yesterday, so you guys are getting it like hot off the press. And it's going to be embargoed in Science, and in 2 weeks from now, you're going to hear a lot. And why you're going to hear a lot? Because the best growing plants are 1% biomass. We're doing biomass, so I can let the bugs just grow exponentially. They're eating hydrogen, that's their only food source. And then they breathe in CO2 and they keep multiplying. They procreate. And that goes into an exponential growth curve, and it's sunlight in, and then I weigh the bacteria, and it's sunlight to biomass yield of 10.2%. But when you have biomass, even with plants, you got to convert it to a fuel. The genomics I just talked about is producing isopropanol at 6.4%, like liquid yield. Light in to like alcohol. And this thing's just excreted out. And then you can collect it. And that's being done in the dark. Huh?
We're back to the horses.
Yeah. But this is good. This is like, so now you could, your diesel, you're not burning diesel, you could burn this, but this is taking CO2. And look, I just want to show you, this is an OD of 2. So a 1 liter reactor at 99% scattering. So that's sort of how much bacteria we have in there. It's fixing 500 liters of CO2 per day because these bugs, just like grass and photosynthesis, have natural CO2 concentration mechanisms in it called carbonic anhydrases. The other way you can think of it, at a 1 kilowatt hour, I'm taking CO2 out of 237 liters of air at 1 kilowatt hour. If you look at, we did the calculation, if you use a means, which you would put in a CO2 stack, we're at 1/10 the CO2 concentration efficiency of the way you remove CO2 from a smokestack. But then you're just with CO2. You got to do something with it. So you could bury it. But here we're at 1/10 and we're going to a liquid fuel. This isn't solving your CO2 problem, right? I just don't want, I'm taking the air out. You burn it, you get the CO2 back. So it's carbon neutral. We're not saving, I'm not going to reverse 400 parts per million CO2, but you're not going to use any more stuff out of the ground. We're not going to add to it. We're just...
Do I get to add 6.4 and 10.6?
No. This is where it's full biomass. Then what I do is here, we let the bugs go into a stationary growth phase, so they're not growing. The amount that are dying or growing, and then I'm using all the excess ATP that I made from my hydrogen from the sun to go into the alcohol.
But you can use it not only to make fuels, you can use it to make materials.
Yeah, like I made plastics.
So that so you'll literally remove CO2.
I think this is a new way to think of a renewable chemical platform for like synthesis.
It's even better than growing more oysters.
I know. I'm kind of excited by this. All right, let me tell you what we're going to do now. Now I need a model to move this, to translate it. So this is what we're going to do, and this is my last few slides. So what some of the stuff in the Paris Accord, 100 billion a year of 2020 to 20 investment in the developing country. That will probably be investment bankers just goofing with money, so I'm not so happy about that. But it was to access and transfer promising renewable energy technologies. So we have this. Harvard has the IP. I just got Harvard to agree to look at the IP as an asset and pass it through to the Institute of Chemical Technology, which is the big chemical engineering institute. I need chemical engineering now to build this. So what would I do usually? Go get investors, start a company, get it, and then try to cram it down India's throat. Say, here, use it. And then nobody does. And my investors want a return on investment because they're from America in 3 years. So now what I convinced Harvard to do is let the IP go to the Institute of Chemical Technology and treat it as an asset. So how's Harvard? Someday, if these guys make lots of money, they're going to have a warm, fuzzy feeling, and they're going to give money back to Harvard. That's how Harvard collects money from all their graduates. That's how you guys. So I'm going to do, that's what we do well, have warm, fuzzy feelings. We are lousy at building companies. So we'll do warm, fuzzy here, and then there are these two characters, one of which you know here. And my hope is they've been doing the CEMS to generate revenue in different models. That's what they're figuring out. My hope is some of that would go there. And the last piece, which I'm going to go to India, is there's some wealthy people I know. I'm going to get them not to invest in Dan's company, but I want them to invest in Indian scientists in India and make it in India. So that's going to be my new model, and we're going to see if it works. I have a cool discovery. It's now got to go to scale up, but I want them to do it. I want to have this integrated sci-tech policy piece to generate revenue for them to develop a really good idea, I think, and then have investors invest in it. So I'm going to see if this is going to work versus the typical thing that we do in the US. And now I said, I'm going to make you guys, I'll feel good, because some of this is grim, and it is grim. And I told you last night at dinner, some of the people there, I'm going to leave you with a great message. And I swear to God, this makes me feel good. I don't know why. So Kurt Vonnegut, just before he died, said, he was doing an interview with David Brancaccio of PBS, and they were saying he had become an environmentalist. And he said, you know, the one thing I can't stand is you guys talking about the planet, the planet, the planet. And what he said is, the planet's a living organism, And like any living organism, it has an immunological response system. So like when you guys get sick, your immunological response system kicks in and it eliminates the irksome intruder when sufficiently compromised. And he said, what you're doing with CO2 is you're being an irksome intruder. Her immunological system will kick in and it will just get rid of you. And as we suffocate the planet in CO2, don't worry, the planet's immunological system will respond and eliminate us all, and the planet is going to be just fine. And I don't know why, that just makes me feel good. No matter what we do, we'll all be dead. The planet is going to be humming along. There may be huge cockroaches. At 1,000 parts per million, there'll be like poison ivy everywhere, but she'll be thriving. So just when you get really depressed, because he's an anti-solipsist. What we do when we think about the planet, we're actually thinking about ourselves. The planet's going to be great. So that's my final message. It should make, when you get really worried, just think about what Kurt Vonnegut said, and you'll just feel happy. I really feel happy when I think about that.
Dan, that was the best